The idea is quite simple, Bashmountain, that I have the positive coming to me here from above. That's the positive. All right, and you have a positive here on what? This is a contact representing for you that there is a contact, you have a command. What command? A command to close your circuit breaker. Nice and good. All right, here's my closing coil, okay? It takes the symbol C. All right, and this closing coil is connected here to the negative. Okay, so here you have the negative and here you have the positive. Is that good? I said to him, great. He said, all right, engineer, if you give me a close, the DC will reach the closing coil with the positive from above and the negative from below. It will act like what we saw in the video, or starting to release and pull your coil, canceling it like that. All right, and there was a column here. Okay, it pulled this column upwards, releasing the mechanism, so the mechanism started to move, and what happened was it closed the circuit breaker. Let me remind you of it so no one forgets. Here it is again. All of this happened when it operated. It pulled this upwards, so it returned what happened to it, and what did it do? It closed again. Here it is. So it closed the breaker again. Here it is. Here it is. It works by pulling this part upwards, which they refer to, for example, the Saudi guys told me before that it's called a dagma. It pulled this dagma upwards, all right? So it started to release the closing spring. The closing spring discharged, and for it, it closed on this mechanism. Let's take a look at it. It pressed on this part. See this mechanism? It pressed on it. So it closed the circuit breaker and charged the spring, charged the trip spring. That's good. I told him, nice. He said, okay, this is your normal one. I told him, okay. He said, okay, this closing coil is an engineer. This closing coil is perfect. DC is connected to it from above and from below. Okay, so our control supply voltage, which is 125 voltage DC, 125 volt DC, this is always your control supply voltage. 125 VDC, 125 VDC is always your control supply voltage, which comes to you from the battery charger. Here the password is 125 VDC, all right, very good. Now the closing spring, engineer the closing, the closing coil engineer, if you apply 125 VDC to it, it draws current. This current depends, of course, on the size of your circuit breaker, whether it is medium voltage, high voltage, or extra high voltage. So you're talking about it drawing approximately, so it will draw around. For example, to DC, of course, is that good? If it draws this current for a longer period, it will overheat, all right? Why, of course, engineer Rashad, because of the video I showed you here. It is a heavy duty. What does heavy duty mean, engineer? It means, look at what it does. See this mechanism? It's massive. The spring is heavily charged, and this part stops the movement of the spring. So it needs a lot of force to pull this lever to release this mechanism. Now, if it remains supplied for a long period, it will burn out. All right, it can't withstand having the supply on it for a long period, right? For a long period. Okay, I told him, great, now I understand. Okay, let's go step by step. Like this, you will close the breaker and 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 close the breaker. The second common for your power cut will receive a DC here. The breaker is already closed, Someone had closed it before and you came to this. This is a close comment again. Do you have a problem? No, of course not, because the breaker was already closed. But do you have a problem if it doesn't give a close comment again? It will give a close. The hand is trying to close the breaker, but it's not closing. He's not even aware that it's already closed. So he keeps trying to close it, thinking there's a problem, that it's not making good contact or not closing properly. As a result, he keeps doing this with his hand several times until the closing coil burns out. That's why. What did he do? He came here before the closing coil and took a contact here. A normal close from the electrical breaker called 52B. First, the 52 is the NC code for the circuit breaker. The NC code for the circuit breaker. We have something called the NC code. It takes numbers from 1 to 94. That's great. Each number means something. For example, if I tell you 24, you'll immediately understand that this means overflux. 21 means distance. 87 means differential protection. 52 means circuit breaker. Each number means something. Differential protection. It means each number signifies something. And it means normally closed contact. Okay, so when is this contact normally closed? The term normally closed must be related to something. When the circuit breaker is open, it means that as long as the circuit breaker is open, this contact is closed. Okay, I told you, great. So if you give me a close command and it goes here to close and the breaker opens, what happens to this contact? It opens. So if you give me a close command again, the DC won't reach the closing coil, which means I protected the circuit breaker from burning out. What is this called, engineer? It's called anti-slam. Look down here as I'm explaining, it's called anti-slam. And this lambda, you cannot give a close command to the circuit breaker if it was already closed, if the electrical circuit itself was already closed, and that by using a normally closed contact, and with the use of a regular motor, a regular ordinary motor, which will open when it happens to it, and thus it means it, prevents, the last or second. So of course this is in English, but let me also come back here and show you as well, here in the part of, all right, here's a part like this. In the situation, actually, as you can see, so I am also in the circuit breaker. I am just waiting to finish what I want to finish so I can give it all to you at once. All right, you will find that I have explained this part here. Here I have explained the anti-slam, which is a contact that is normally closed when the circuit breaker is open and open when the circuit breaker is closed. This is to prevent the closing command, which is the positive, from reaching the closing coil when the circuit breaker is already closed. This is to prevent the closing coil from burning out completely, as the closing coil draws a high current, as I mentioned to you, and it cannot withstand this current for more than 5 seconds. So when the circuit breaker is mechanically closed, there is no problem. But if you accidentally connect DC to the closing coil, it will draw current without changing its position, and as a result, it will burn out. Is that clear, engineers? This concept is called what? We call this contact function anti-slam. What is it called? Anti-slam. All right, this is the part famously known as the anti-slam story. So the 52B is the anti-what? Anti-slam. Engineers, focus with me on these concepts, because for those who have booked the test for this course, I know that questions like this might come up. All right, Engineer Fairs asks me, what are the reasons for the burnout of the closed coil other than the anti-slam? Okay, I'm about to discuss that. So the first anti-slam won't burn. The anti-slam is made so it doesn't burn, or the closed coil doesn't burn by ensuring that you can't give another close command if the breaker is already closed. All right, great. So I closed the breaker, gave it a close command, and the breaker was open. So now it's closed. I gave a close command and the DC reached the closing coil. All right, the breaker closed and I'm about to continue discussing this. Okay, engineer, the closed coil was activated and the breaker closed. When the breaker closes, what happens? It opens, right? And the point, right? For some reason, if the close command remains stuck, we don't return to the previous state. What does it mean when I close the discrepancy switch? Okay, and I removed my hand for some reason, and it got stuck in a place and didn't return to the normal state. Or I close it using the latching mechanism or the SAS, which is the PSA, or through the PCO, and the output contact from the PCO closed, and for some reason didn't open. The contact might have broken, the contact got stuck, and it remained stuck together. The important thing is that it remained latched. Latched means it got stuck, meaning it stayed permanently closed. Stuck, meaning, okay, so the positive remained always present here. Do you have a problem? No, I don't have a problem. Why? because this contact is open, so there's no DC going to the closing coil. But if this breaker opened due to a fault or whatever reason, it opened. As soon as it opens, this contact returns to normally what? Normally closed. So as soon as it returns to normally closed, it finds a boost in its face again, and it closes the breaker once more. Was the breaker supposed to close? No. Okay, that's number one. Now the breaker closed because the fault that caused the breaker to trip is still present because you haven't fixed anything yet. The breaker just opened and closed again, and then the breaker will open again. What happens next? It returns once more. It finds the boost present, right? Am I wrong? So it closes the breaker again, and the breaker closes, right? We said, am I wrong? So the breaker keeps closing and opening. Okay, it finds the boost. So it closes and keeps operating in this manner. All right, very good, engineer. What does this mean? This means the following. The breaker will now keep closing and opening, closing and opening, closing and opening. Before I continue this sentence, let me clarify something else. Now, engineer, like this example, let's assume that the breaker itself is fine, but the spring for the closing is not charged. And you gave the close command to the breaker. So if you gave the close command to the breaker, mechanically, the breaker will not close because the closing spring is not charged electrically correctly. You are connecting the boost in the slope to the close, so you will burn it. Right or wrong? You told me right. I told you. So I have to come here and take a normal close contact called LS3 from the spring state. Spring CB spring, named to S3 from aspirin case aspirin. It is fully charged, meaning as long as the spring is charged, this contact is closed. If the spring is not charged, this contact is open. So if you give a close command, the DC won't reach the close coil to prevent it from burning. This is the second reason. The first reason is if you give a close command to a breaker and the breaker is closed and you try to give another close command, you might wonder why the breaker isn't responding. You're giving a close command, thinking the contact isn't making good contact, but at the same time, you're giving. The result or solution is that I created a normally closed contact from the state of the circuit breaker and called it anti-slam. This contact is closed if the breaker is open. And if the breaker closes, it opens to prevent a second close command from reaching the breaker if it is already closed. Okay, and you have this normal close contact. It's normally closed when the spring is charged. So as long as the spring is charged, it keeps giving a close command. If the spring is not charged, this contact opens. So it keeps giving a close command, but the breaker mechanically won't close at all. So there's no need to connect the close command to the closing coil because it might burn out since it won't close mechanically anyway, right? Oh, am I wrong? Right. So what do we take here? Contacts, exactly. Now, let's go back to the previous step with the presence of these two. With the presence of these two, let's complete the full scenario. You gave a close command and the latch is engaged, meaning it's always connected here. Okay, the spring is charged, yes, so this contact is closed. The breaker is open, yes, so this contact is closed, connecting the positive here and the negative from below. So the breaker closes. The breaker is closed, right? Let's assume after a while, the breaker opens. The breaker opens and this contact returns. Of course, when the breaker was closed, this opened, right? And when the breaker closed, the spring became discharged. So this opened, meaning no DC will reach here after the spring charging time, which is about 5 to 10 seconds. This contact returns to close again because the spring is charged. And this remains open because the breaker is already closed. The breaker opens, this returns to close, and this closes. A command comes here to close, so the breaker closes as soon as the breaker closes. A fault will occur. The fault is present, so the breaker will open again. This will close, but this hasn't closed yet because the spring is still charging, so it continues to charge. Once it closes, this closes and that closes, the DC reaches and the breaker closes. The fault is still present, so the breaker opens and this remains closed, and that. What will happen to this? The breaker will still be charging, and after it finishes charging, it will close. Yes, so what you're saying, Bash phones Rashad, means the following. If I close the breaker and the close command is still hanging, it means don't pull. And if the breaker closed and opened due to a fault, it will keep closing and opening repeatedly. No, it will close and open every 5 to 10 seconds because each time it closes, the spring mechanism charges. So every 5 to 10 seconds, it starts receiving DC. So naturally, at close intervals of 5 to 10 seconds, you supply DC to the coil. The coil, of course, draws current to release its latch, and naturally, due to the passage of a 3 amp current through it, it will heat up slightly. Every 5 seconds, you keep supplying it with current. Every 5 seconds, you supply it with current, and with the frequent passage of current through it, it will burn out. That's one thing. The second thing, Engineer Rashad, is that this circuit breaker keeps closing and opening, closing and opening. And it's not just closing and opening normally. There's voltage here and supply there. So when you open and close, there's an arc. You're constantly opening and closing on an arc, opening and closing on an arc at close intervals. These poles will heat up and explode. The third thing is that the breaker keeps closing and opening every 5 seconds. As a maintenance person, they informed you, and you're heading to the station, which is an hour away. Imagine during that hour, every minute has how many 5-second intervals? It has 12 5-second intervals. So the breaker will be closing and opening 12 times in 60 minutes, which is 720 times, 720 times on the arc. And 720 times the spring is charging and discharging, and 720 times you're reaching the relay. What is this DC in the case that you reached in an hour? In this situation, your spring will be damaged. The poles of the breaker will be damaged. The closing coil might also move. So what should I do, Engineer Rashad? Here we do something called anti-bombing. The anti-what? The anti-bombing. Bombing? The anti-what? The anti-bombing? All right, so where's the idea in this anti-bombing? What does it start doing? It comes here, inside the circuit breaker itself, and installs another coil here, or an auxiliary relay, a very small auxiliary relay. Those who attended the circuit breaker maintenance course with us saw it last time. A small coil, just a regular coil. Okay, good. So what does it do with this coil? Focus with me. It comes here from the DC and moves like this. It comes and tells you that as soon as you close the power cut, what happens? Doesn't the limit switch of the spring open as a result of the spring discharging? I said yes. He said, okay, I will also take the limit switch S3, take another contact, all right, very good, and connect it here to this code. So as soon as you close the power cut, this one opens and this one closes, all right. Okay, after the spring charges, this will return closed and that open, right? So I will make another move. Didn't this close and activate the Y wire? Yes, he told me to take a contact from this same Y, which is a normally open contact. But you have to say, what is this, Engineer Rashad? When this opened and that closed, after you closed the breaker, the spring discharged. So this opened and that closed, connecting the DC here. Now, there is a positive here and a negative from below. So this worked and closed on itself, and the situation remains like this, always closed. This received a supply. So what did it do? It performed something called self-latching, meaning it latches itself or holds itself. We call it self-latching. I told him, great. So what did you gain from this? I gained from this, but when does it reset? Okay, since it's working on its own, it will never be able to disconnect itself unless it disconnects itself. So who is operating it? It means we are going in an infinite loop here. The only way to disconnect this circuit is to cut off the supply above, right? Am I wrong? I told him, right. He said, as long as this supply is connected, this Y is working. So it comes here and takes a normally closed contact from this Y like this. A normally closed contact from this Y, is it like this? So I made this dotted plan, meaning that this is part of that. And it takes a contact here called YB, for example. Great. It takes YB. So as long as this is working, it opens the path here. As long as the DC is hanging here, as long as the DC is hanging, this path remains open. So even if the breaker closes on a fault and opens, and this returns to close, and this returns to close, the path is cut off through this. This is called anti-bombing. What is it called? Look with me down here. Look below. Anti-bombing, anti-bombing. It is a device. Exactly, a device. a device, okay? It's a device. The circuit breaker, whose function or job is to prevent multiple breaker closures. Of course, this is a bit of English, so if you're not very fond of it, you can read the anti-pumping here. I'm telling you, you'll find a mix of formal and colloquial Arabic here, so don't be upset with me. Take what you can from it. I'm telling you, if you give the circuit breaker a close command, which is the close command, okay? And for some reason, this close command continues. It continues, meaning it remains stuck due to the discrepancy switch or contact being stuck on the PCU. After the circuit breaker closes, if it opens again due to a fault, for example, what will happen is that due to the continued presence of the DC, on the closing circuit, the circuit breaker will close again. And of course, since the fault itself hasn't been fixed, the voltage is still present, it will open again. But of course, this opening and closing process will happen every approximately 10 seconds, which is the charging time of the S brake, which is specific to the closing operation. This process could lead to the burning of the closing coil and damage to the mechanism. Also, as a result of closing and opening on a fault, this arc could destroy the poles of the circuit breaker. This is what is referred to as anti-pumping. Therefore, when the circuit breaker closes, the anti-pumping mechanism latches onto itself and it cuts off the DC path, specifically the positive, from the closed coil and remains in this state as long as the positive is continuously applied and present on the closed circuit. So I have now explained to you the concept of the anti-pumping mechanism. Yes, your anti-pumping is fine. So now we have anti-pumping and you, Islam. Okay, there's a part here, Bash and Andes. You leave it open below. Yes, you see the SF6 gas. I'll tell you about it, and I'll tell you here, Bash and Andes, you have something called LS1. LS1, this LS1 Bash and Andes Russia, this LS1 Bash and Andes tells you what? It tells you if you come here and look, for example, in this video about the circuit breaker itself. Let's slightly shrink this screen a bit. Here you go, this breaker, engineers. Here you have carefully inserted it into the cell, right? Very good. You decided to rack it in, or it was racked in, and you decided to do what? To rack it out. So whether you rack it in or rack it out, as soon as you start to make a move, as soon as you make a slight movement to rack in, or it was racked in and is coming out to rack out, here engineers, now what will happen? What actually happens is that in the circuit breaker, the breaker itself becomes different. Mechanically, you won't be able to close it, meaning you can't close it. If I'm looking at the breaker from the side like this, here's the circuit breaker. It has wheels here and wheels here. I'm looking at it from the side, right? Okay, and this breaker moves along the track of the cell itself, right? Very good. Here, engineers, there is a hole. And here, there is a hole, exactly, a hole with an opening, exactly. And here there is an opening, all right? A normal breaker, completely rack in or completely rack out. If it's like this, completely rack out, exactly. It's rack out like this. But if it's rack in, you'll find the breaker comes in like this. Like this. So you'll find this wheel came here. And this wheel, here it is in front of us, came here. Let's mark it in red like this, and in red like this, exactly. So whether the breaker is rack out or the breaker is rack in, here is the front of my cell, here it is. So it's rack out and goes inside as rack in, or it's rack out and you came to close the electrical breaker. There's a pin here that goes down into this hole, preventing the movement of the breaker rack in. And if it is rack in and you close it, the same lever goes down here into this hole, preventing mechanical movement in the direction of rack out. This prevents mechanical movement in the direction of rack in. So as long as the breaker is closed, its movement is prohibited, whether rack in or rack out. Because engineer, you can't have your electrical breaker closed like this and then try to rack it in. Well, here there is a supply and here there is a load. You can't do that. And as you bring the breaker closer to the supply and load, an arc or spark will occur here. That's why you must insert the breaker rack in and then close the electrical piece. At the same time, you can't have it closed and pull it out because a spark will occur here. And a very large arc could happen, which might explode. Also, that's why you must pull it out, rack out first, so you open it first, Then you pull it out, rack out. So when you open it, it means here is just the supply, and here is the supply. Each unit is separate and not connected. But if they are connected, an arc will occur here. Why? Because it tries to cut or break the insulation to deliver electricity to your load. Very good. So now, if the breaker is in between, this lever, engineer, you open the breaker, so this lever is pulled up now, right? The breaker is in between here. So when you want to do what? You want to close the breaker while it's in between. When you try to close it, you'll find this lever hits where? In the groove, so you won't be able to close the breaker. So mechanically, you won't be able to close what? Close the breaker. Now, if someone comes and the breaker is in between, or the breaker is not totally racked out, or totally racked in, meaning it hasn't been fully inserted or fully removed, and someone comes and tries to close it without realizing that it's neither totally racked in nor totally racked out, the breaker won't close. They'll keep trying to operate the switch, wondering why it won't close, until it gets stuck and burns out. That's why there's a contact here called, this is a limit switch. What is this limit switch? Bashan's Rashad. By God, I am Bashan's Rashad, just like you. I open the drawing board and feel it. If I am simple here in the drawing board, I will find that LS1 is the closing interlock limit switch. The interlock limit switch, only with dropper type. What does that mean, Engineer Rashad? It means that if the breaker is not totally racked out or totally racked in, this limit switch opens to cut the negative path to the closing coil. Therefore, even if you give a close command, it won't burn the closing coil. Mechanically, the breaker might close, but electrically, if you keep applying DC to the closing coil, it will burn. That's why if the breaker is neither totally racked out nor totally racked in, the limit switch starts to open to prevent the closing operation or to connect the DC to the closing coil so that the closing coil doesn't burn. Will the breaker mechanically close, engineer? No, it's impossible for it to close at all. Why? Because mechanically, it considers the mechanical interlock process. But electrically, it would have connected DC to the closing coil, burning the closing coil of the circuit breaker. Is that clear, engineer? Great. Now let me get back to you. Are you tired of me yet? So I'll get back to you again. All right, very good. So now I understand this entire circuit, and I have one last contact left. If my breaker is of the Schneider or ABB SF6 type, meaning it's not a vacuum circuit breaker, it would be an SF6 circuit breaker. SF6 circuit breaker or oil circuit breaker, my dear engineers. There is the SF6 circuit breaker, or the engineers, it would be in gauge. What does gauge mean, Engineer Rashad? It means meters, all right, or meters are in a gauge, engineers. On the breaker like this. Let me draw it for you like this. This gauge, engineers, measures the pressure of the SF6 gas inside the tube you saw, which contains the arc extinguishing medium. So when the gas pressure, you might ask, why the gas pressure? Yes, engineers, the SF6 gas, which is a type of circuit breaker that operates with SF6 gas known as sulfur hexafluoride. For this type, in order for the SF6 gas to provide insulation, the gas must be pressurized. Typically in medium voltage, it is around 2 bars. When the gas pressure decreases, it means that the gas has lost its insulating properties. Consequently, it no longer acts as an insulator. Therefore, if the breaker closes or opens, a spark will occur, and there will be no medium to extinguish the spark, or the existing medium will have low pressure, resulting in poor insulation. This will cause the arc to form and persist for a long time, potentially causing issues with the breaker. That's why it starts to make contact here. This gauge, according to the gas pressure, has a set of limit switches. The limit switch is what I placed here, so that if the gas pressure is low, it opens the circuit here, preventing the circuit breaker from closing. Sorry, it prevents the circuit breaker from closing, because forming the arc would destroy the circuit breaker. At the same time, if you close the breaker and the gas pressure is low, a fault might occur, and the breaker will try to open. This also happens during a fault, meaning a current in kiloamperes. So imagine you're interrupting the spark of a kiloampere current. What would happen then? So where do I get this contact from? I get it from the L6 gauge. The L6 gauge.